Hey everybody, I want to show you one of my favorite things to play with when I was a kid.
Air jammer, road rammer. Pump them up and let them go, and when they go, they don't go slow. Air jammer, road rammer. Air jammer, road rammer. It's a car that runs on air, no batteries or gas in there. Air jammer, road rammer. Air jammer, road rammer. The Air Jammer Road Rammer comes with a pump. Is made by Tomy.
Check it out, I still have mine. And here's how it works. You've got this large for a 6-year-old, container that you fill with compressed air. And you compress it with this air pump. And mine no longer works, but what you would do is you would connect the air hose from this part of the air pump to the back of the vehicle here, and you would fill this tank. Again, all the work that you're doing is going into compressing the air inside this tank. And then when you were ready to go, it took a little bit of activation energy, but you would push this thing, or if you saw in the commercial, they'd spin one of the wheels, and that released this piston in the back, which you can kind of see going up and down. It's got a small crankshaft. And let's see if we can get this to focus better. And this small crankshaft, you can see it right down there, is connected to the rear axle. And as the wheels spin, as the connecting rod moves up and down, it actually spins the wheels. And the trick is that you would load this up with enough compressed air, and the more compressed air, the more work you put into it, the faster it would go and the farther it would go. So let's see what's going on. We're going to take a look at how this translates to work, energy, and how we can change the volume inside of a cylinder with a movable piston. So how does this work? So before we can get into how compressed air moves a piston, we need to look at what we're going to call work, heat, energy, and something called the first law of thermodynamics. Well, if we were going to look at the first law, let's look at all of them. So here they are. And the first law says that energy can never be created or destroyed. And that's pretty familiar. We know that energy can be transformed from one form to the other, but it always has to go somewhere. It doesn't just disappear. And this second law of thermodynamics, we're going to pay attention to this because it breaks up the energy of the universe into something called the system and the surroundings. But we'll get to that in a little bit. Right now, let's focus on this guy. And what this says is that the change in energy has to be equal to Q, which is the heat gained or lost by the system, and work, W, which is the work either done on the system by the surroundings or done on the surroundings by the system. Let's take a closer look at these two. So let's look at this first metric, Q. You might remember seeing this from specific heat when we did specific heat way back in honors chemistry. Specific heat is equal to Q over M times delta T. Well, that's where we first saw Q. And we're going to represent it a couple different ways. In an endothermic reaction, this means that the system, in this case, the system will mean the reaction that we're talking about. And so in an endothermic reaction, the system, the reaction is absorbing heat from the surroundings. This means that heat must be added. And so we're going to abbreviate a system that absorbs heat as positive Q. That's an endothermic system. We have to add energy from the system to the system from the surroundings. And conversely, an exothermic reaction means that the system releases heat into the surroundings. This is going to be negative Q. So let's pay attention to the sign of our heat transfer. Now let's take a look at what we're going to call work. We're going to also measure work in joules. If you remember from physics class, work has its own formula. It's equal to the force exerted multiplied by the distance over which that force is exerted. And we can have the system do work on the surroundings, meaning the reaction causes the surroundings to change, or we can have the surroundings do work on the system, and the sign of our work value will determine which direction. So if we have a situation where the system, otherwise known as the reaction, does work on the surroundings, our sign for work is negative. The way I keep this straight is that work is leaving the system. If the surroundings, meaning the environment, do work on the system, meaning the reaction, then the sign of our work value is positive. In other words, work enters the system. And at all times, we have to be considering this first law of thermodynamics, that the total change in energy of the universe, of the system, of the surroundings, the whole big picture, is equal to Q plus W. Let's try one. This is an example that comes right out of your text, and we're calculating delta E in joules, in this case kilojoules, with this simple equation. Let's keep in mind the sign of each reaction, so let's take a look at A first. And so we have Q equals negative 47 kilojoules, and work is positive 88 kilojoules. Let's remember that because in this case our energy is negative, our system is giving off energy to the surroundings, meaning it's an exothermic reaction, and because our work sign is positive, it means that the surroundings are actually doing the work on the system. So the overall work of the system is increasing. So let's calculate this. Delta E is equal to negative 47 kilojoules plus 88 kilojoules. And let's bust out our handy calculator. I know we can do these things in your head, I know that, but sometimes you don't want to risk it. So negative 47 plus 88, and in this case the overall delta E of our universe, in this case system and surroundings, is, and I closed that before I actually read the answer, positive 41. Keep in mind your sign. That means that overall the energy of this particular systems and surroundings is increasing. And let's do B. We've got a Q of plus 82 kilojoules, and we've got a work of negative 47. Because the Q is positive, it means our reaction is absorbing energy. It's an endothermic reaction. And because the work is negative, it means that the system is doing work on the surroundings. So let's calculate it. Delta E equals positive 82 kilojoules plus negative 47 kilojoules. And you might think that this is a rather elementary way of going about it, but you want to keep your numbers straight as much as you can. So we'll say we have 82 kilojoules, and we're going to add to this negative 47, and our answer is 35. Again, an overall positive energy change. Keep this sign as straight as you can. So let's get back to this guy. How is it that we can take work done on this end and have it come out on this end? So let's take this equation from physics, where work is equal to force times distance. And we're going to flip this equation around a little bit. And if we have already taken a physics class, we might have seen that the formula for pressure is equal to force over area. And I don't think that you guys are that concerned about how we get the equations. And so if you are interested, we'll keep this in mind, that this area part is going to be the distance our piston moves. So our equation for work, as far as it applies to a system like this, where we are moving a piston as a volume of air expands or contracts, it works like this. Work is equal to the pressure exerted times the change in volume. And our unit for pressure is, of course, always going to be atmospheres. And our unit for volume is liters. And so work is going to be measured in a strange unit. It's going to be the liter atmospheres. And as far as we are concerned, 1 liter atmosphere is equal to 101.3 joules. So it's a fairly straightforward way of converting from joules to liter atmospheres. And we want to make sure we take and consider one more thing. Because our delta V is increasing, that means that the system has to do work on the surroundings. Well, if we go back up here, if the system does work on the surroundings, work has to be negative. So we're going to do one more modification to this equation to make the work be negative. Either negative work equals positive pressure times delta V, or, as in our cases, work will be equal to negative pressure times delta V. Let's try one of these, and we'll see how the units crank out. All right, let's be careful when we see a problem like this, because it comes with its own built-in curveball. Let's remember that our formula for work is equal to negative P, being pressure, times delta V, being change in volume. And so we want to calculate the work. Actually, it already gives us this work we have. Our work is 210 liter atmospheres. It also gives us a delta V where we go from 10 liters to 25 liters. So our delta V is 15, and it wants us to calculate the pressure. But be careful, because it says at the same time 45 joules of heat are transferred from the surroundings to the system. This equation to solve for pressure doesn't have any part to deal with Q. So this is something that we can ignore. Be careful when you see this. It's not necessary to solve a problem like this. What is important is that we want to keep in mind our units. And what's nice about this one is that we don't have to worry too much about it. So let's say that we have a work of 210 liter atmospheres. This is equal to negative P. And let's keep in mind that our volume is expanding. So if our delta V is positive, let's be careful how this works. So delta P times positive 15 liters. So let's bust out our calculator, and we're going to solve for delta P. And it says against what pressure is the system working. So let's be careful of the sign. Solving for P, we get 210 liter atmospheres equals negative P divided by 15 liters over here. Now, as we're doing this, let's be careful, because it says the piston performs work of 210 liter atmospheres on the surroundings. And let's be careful, because what sign are we talking about if the work performs system on the surroundings? That's negative. And so what's cool about that is that that will eliminate the negative sign from our pressure. So let's bust out our calculator. We know that liters is going to cancel. Our negative signs will cancel. Our answer will be in a positive number, which is what we want. You really can't have negative pressure less than a vacuum. And so busting out our calculator, we're going to say, and my calculator won't turn on, so make sure you have a backup. Mine's way over here. Sorry about that. 210 divided by 15. Let's get rid of this piece of crap. And our new pressure against which our piston is working is 14 atmospheres. And we've seen how the units cancel and how the signs take care of everything. So let's be careful. The work was done on the surroundings by the system. That's negative work. All right? So, see you guys on the next one, and let's take this for a spin.